Okay, now I want to distinguish between points on a transverse wave that are in phase versus out of phase. Now, in phase means that these points are going to have, so any points that are in phase, any points in phase will have the exact same displacement at the same time. Meaning they're going to oscillate the same distance and in the same direction as one another. Okay. And these are always going to be full lambda apart. So it could either be 1 lambda apart, 2 lambda apart, 3 lambda apart, and so on. Now this could mean 360 degrees, 720 degrees, ... and so on. Okay, so any points that are separated by that increment of degrees are going to be in phase with each other, meaning they'll be oscillating in the same direction at the same time. Okay, so let's figure out some of the points that are in phase with each other. Well, let's see if there's any point that's in phase with point A. Well, we know we need something 360 degrees apart. Let's see. So we have, this would be 45 degrees apart, 90. Right? 135. 180. This is going to be 270, 360. Okay, so A and G are going to be in phase with each other. What that means is that whatever A is doing, G is also going to be doing as this wave gets propagated. Okay, well, let's see. Does B have any point that's in phase with it? Well, from here to halfway, we have 90 degrees. So from here to B, we really have 45 degrees. So we want to see if we can find one full wavelength away from B, or two full wavelengths, let's say. So we have 45, 90, 180, 90, 180. That's one full wavelength apart, right? B and H are in phase with each other, meaning they're going to have the exact same displacement at the same time. Okay, so by the way, we didn't check A with J, and we probably should because those might also be in phase. Well, we have 90 degrees, 180, 270, 360. That's 1 lambda. 90, 180, 270, 360, 2 lambda. That qualifies as being in phase. So we got to add A and J. Those are in phase with each other. Let's see if there's anything else that's in phase. Well, we haven't looked at C at all. Let's start at C. So we have 90 degrees, 180, 270, 360. So C and I are 1 lambda apart, which means they're in phase with each other. So C and I are also in phase. And that looks like it's it for all of the in phase points. So now let's talk about what it means to be out of phase. Well, if 2 points are out of phase, these points will have the exact opposite displacement at the same time. These points will have the exact opposite. So the sign will be different. The directionality will be different. The distance will be the same, but the directionality will be different. So the exact opposite displacements, meaning that it's the same magnitude, opposite direction. Sorry, I'm abbreviating. Okay. And these out of phase points, instead of being one full cycle apart, like the in phase points, will actually be half a cycle apart. In other words, 0.5 lambda, 1.5 lambda, and so on. Okay? So what we're talking about here is going to be 180 degrees apart, and so on. So I want to just look, again, starting from point A and see if we can find any out of phase points. Well, A and G were in phase, so let's look at A and D. Okay, because to me they look like they're out of phase. So we have 90 degrees, 180 degrees. Yes, they are. So A and D are out of phase with each other. Okay, they're only half a cycle apart. By the way, A and G were in phase. So if A and D are out of phase, we should check D and G, right? 90, 180 degrees. Those are also out of phase, D and G. Now I'm realizing something. We never got G and J as in phase, right? So 90, 180, 270, 360. So let's add that to our in phase list. G and J. Sorry, I missed that. Okay, so back to out of phase. Let's look. Is there anything else out of phase? We got A and D, and we got D and G. Okay, good. Let's see what else. Is there anything out of phase with point B? Well, we have 45, 90, another 45, 180. Well, B and E are doing the exact opposite thing at the same time. Those are out of phase, those points. B and D. Okay, let's look at C. We have 90, 180, C and F. When C goes up, F goes down. Okay, when F goes back up, C will go down. So C and F are out of phase. C and F. Let's see what else. Well, it looks like also F and I, right? So 90, 180. So F and I are also out of phase. Let's see what else. So B and E. Let's see if we see anything with E. Okay, so we have 90, 180. So E and H are out of phase with each other. Okay, so this is the gist of how you would assess whether or not points are in phase or out of phase. If they're not exactly 1 lambda apart, they're not in phase with each other. If they're not exactly half a lambda apart, they are not out of phase with each other. Okay. The other thing that I want to do before moving on is we never talked about electromagnetic waves yet, and electromagnetic waves are a fancy way of saying light. Now, light we're going to get into a lot more when we do the modern physics unit, but it's really important to know that light waves are not fully understood yet. What is understood about them, while some people classify them as transverse waves, some classify them as transverse waves. I tend to give them my own category because I think that because they don't require a medium, I think it's fair to give them their own category. So light waves are interesting because actually they have a sort of two-part waveform. The first part of the waveform is you have this oscillating electron. And that oscillating electron generates an electric wave. Okay, so this green thing, we can consider our little oscillating electron. In other words, the green is our electric wave. But anytime we have a moving electron, we're generating a magnetic field. So special or unique to an electromagnetic wave is actually perpendicular to this. You're going to have this magnetic wave being generated perpendicular to the electric wave. So it's been a while since I've drawn this, so forgive me if it comes out not that great. This isn't coming out good. Okay. Anyway, I'll try and redraw this for you guys in a little bit. Let's see. Didn't come out good. It's kind of hard to do, I'm not gonna lie. Anyway, so perpendicular to our electric wave, there's actually this magnetic wave. So here we have a magnetic wave, which is perpendicular to the electric wave. And unique to light also is that the frequency is associated with how much energy is being transferred. So higher frequency of light is associated with a greater energetic transfer. Greater energetic transfer. And we will get into this in the modern physics unit. Okay. And again, the speed of light is 3 times 10 to the 8 meters per second, in contrast to the speed of sound, which is only 331 meters per second, and both of those pieces of information are in your reference table.